Welcome to our exploration of Bohr's revolutionary atomic model and the Rydberg Constant. Today we'll discover how Niels Bohr solved the mystery of atomic structure in 1913. Bohr's atomic model was groundbreaking because it successfully explained why atoms are stable and why they emit light at specific wavelengths. Before Bohr, scientists couldn't explain why electrons didn't spiral into the nucleus or why hydrogen produced distinct spectral lines. We'll cover Bohr's postulates, energy quantization, electron transitions, and how this leads to the famous Rydberg constant. This diagram shows Bohr's model with electrons moving in fixed circular orbits around the nucleus, each orbit corresponding to a specific energy level. Bohr made three revolutionary postulates that changed our understanding of atomic structure forever. First postulate: electrons move in circular orbits without radiating energy, which solved the stability problem of atoms. Second postulate: angular momentum is quantized in multiples of h-bar, restricting electrons to specific orbital radii. Third postulate: energy is emitted or absorbed only when electrons jump between these allowed energy levels. The angular momentum L equals n times h-bar, where n is a positive integer and h-bar is Planck's constant divided by 2pi. The energy of the nth level is negative 13.6 electron volts divided by n squared, showing that energy becomes less negative as n increases. This energy level diagram shows the quantized orbits with n equals 1, 2, 3, and 4, demonstrating how energy levels get closer together as n increases. When electrons transition between energy levels, they emit or absorb photons with specific energies, creating the hydrogen emission spectrum. The energy difference between levels determines the photon energy and therefore the wavelength of emitted light. The energy of an emitted photon equals the difference between the initial and final energy levels, which is 13.6 eV times the quantity 1 over n final squared minus 1 over n initial squared. Using the relationship between energy and wavelength, we can calculate the exact wavelengths of spectral lines. Since energy equals hc over lambda, we can solve for wavelength. 1 over lambda equals the Rydberg constant times the quantity 1 over n final squared minus 1 over n initial squared. This spectrum shows the hydrogen emission lines organized into series: Lyman series in UV, Balmer series in visible light, and Paschen series in infrared, each corresponding to transitions ending at different energy levels. The Rydberg constant emerges naturally from Bohr's model and represents one of the most precisely known physical constants. Starting with the balance between centripetal force and Coulomb attraction, plus the quantization condition, we can derive the Rydberg constant. The Coulomb force provides the centripetal force, K times E squared over R squared equals M times V squared over R. The quantization condition states that mvr equals n times h-bar. Solving these equations simultaneously gives us the orbital radius and energy levels. The Rydberg constant equals m times e to the fourth power times k squared, all divided by 2 times h-bar squared times h times c. This diagram shows the step-by-step mathematical derivation, starting from force balance and quantization conditions, leading to the final expression for the Rydberg constant. The hydrogen spectrum is organized into distinct series, each corresponding to transitions ending at a specific energy level. The Lyman series results from transitions to n equals 1, producing ultraviolet radiation. For Lyman series, 1 over lambda equals RH times the quantity 1 minus 1 over n squared, where n is 2, 3, 4, and so on. The Balmer series involves transitions to n equals 2, producing visible light that we can see. For Balmer series, 1 over lambda equals RH times the quantity 1 over 4 minus 1 over n squared, where n is 3, 4, 5, and so on. The Paschen series corresponds to transitions to n equals 3, producing infrared radiation. This comprehensive spectrum shows all the hydrogen emission lines across ultraviolet, visible, and infrared regions, with each line labeled by its transition and calculated wavelength using the Rydberg formula. Bohr's model, while later superseded by quantum mechanics, remains fundamental to understanding atomic structure and has countless modern applications. Bohr's model successfully explained the hydrogen spectrum and introduced the concept of energy quantization to atomic physics. It provided the first successful quantum model of the atom and established the theoretical foundation for spectroscopy. Today, the Rydberg constant is used in precision measurements, atomic clocks, and fundamental physics research. Spectroscopy techniques based on Bohr's principles are used in astronomy, chemistry, and materials science. The Rydberg constant is now known to extraordinary precision, 1.097373156816 times 10 to the 7th inverse meters. If you found this exploration of Bohr's atomic model fascinating, please like this video and subscribe for more physics content.